Okay, so here we're going to look at another set of exercises, and it's going to just use one function here that they give us, and we're going to answer these 6 questions. So this is about the population of a fish farm in T years is modeled by the equation P of T equals 1,000 divided by 1 plus 9 e to the negative 0.6t, and we're using a calculator to do a lot of this work. So first thing it wants us to do is graph the function. All right, so to graph the function, what do? We go over here and we make sure we type in the function correctly, which I've done already to save time. And we can see it graphs, and it's the logistic function. It comes up and it gets to the point where it reaches the horizontal asymptote at y equals 1,000, and then it gets close to but never actually comes touching it. And so that's going to be what the function looks like. So now that's basically part 1 of our question here. So now 18 is, what is the initial population of the fish? Well, we can do that in 2 different ways. We can look at a graph and see what is t0. And if we do that, what we can do is we can say trace, and we want it at 0, x equals 0, and it says it's equal to 100. And so that's one way we can get it really quick. And so we can say, well, that's equal to 100. The other way is we can take our function here and say we want to find p of 0. Well, that's going to be 1,000 divided by 1 plus 9 e to the minus 0.6 times 0. Well, e to the minus 0.6 times 0 is just going to be 1. So we have 1 plus 9 is 10. So we have 1,000 divided by 10, which is also 100. So both of them give us the same answer. One of them we had to do a little bit of work. The other one we just told the calculator to do the work for us. All right, so the next one is asking to the nearest tenth, what is the doubling time for the fish population? All right, so where do we go with that one? Well, we have 19. And so what we remember is t is equal to ln of 2 over k. So that's how we do the doubling. It's going to go up and it's doubling. So we have the positive of this. And so here we have k. Well, what is k equal to? Well, k is going to be equal to, in this case, a negative ln of the b. Well, what was b? Well, b is negative 0.6. So that's equal to negative ln of 0.6. And so what we can do is we can just take and plug that in here. And so t is equal to ln of 2 divided by a negative ln of 0.6. And if we plug that into our calculator, what we get, if we go here, we get the ln of 2 divided by the ln of 0.6, and that's supposed to be the negative ln of 0.6, so we better insert a negative here. Oops, wrong place for the negative. We want the negative here. And then we can go here, close parenthesis, enter, and we get 1.3569. So that's equal to 1.3569, which is approximately, when we do to the nearest tenth, 1.4, and these are years. Okay, and so that would be our answer for number 19. All right, so we've got that one done, and 18, so now 20. To the nearest whole number, what will the fish population be after 2 years? Well, that one we just have to find what P of 2 is. So P of 2 equals, now we just take 1,000 divided by 1 plus 9 e to the negative 0.6 times 2. And if we plug that into our calculator, what do we get? Well, let's go back over to our calculator, and we're going to have our 1,000 divided by, and we'll put 1 plus 9, and then it's e to the negative 0.6 times 2, arrow down in parentheses, and so that gives us 269.48. And so what does that give us here? It's going to be 269.48, and we want it to the nearest whole number. And so I'm going to say, because we want to go up, that's going to give us 2 70 fish approximately. Okay, so it's going to be, we won't round down because you can't round down to a lower fish, so we'll round up to the nearest fish, and that's going to be the 270. Okay. All right, so the next one, to the nearest tenth, how long will it take for the population to reach 900? Well, what do we have to do here? Well, now we know what this part is. We know the P of T, and we're going to look for T. So for 21, we're going to say 900 equals, then we have 1,000 over 1 plus 9e to the negative 0.6 t, and we have to solve for t. Well, I'm going to multiply both sides by the 1 plus 9e to the negative 0.6 t. So on this side, it's gone. So on the other side, we're going to have 900. 900 times 1 is 900. Then 900 times 9 is going to be plus 8100 e to the negative 0.6 t. And that equals the 1,000. Now we'll subtract the 900. And so now we get 8100 e to negative 0.6 t equals 100. And so now we have to get rid of the 8100, so we're going to divide both sides by 8100. And so now what we have, if we get our space up here, that's going to give us e to the minus 0.6 t equals, now 2 zeros cancel here, 2 zeros, so we get 1 over 81. Now we're going to take the log of both sides, and it's going to be the natural, so ln, so we get a negative 0.6 t equals, and the ln of e is just 1, so we can drop it, and then we have ln of 1 over 81. Now we divide by a negative 0.6, and so t is equal to, now if we plug that into our calculator, and then we had, what was what, ln of 1 divided by 81, then that whole thing divided by a negative 0.6. So that looks like 7.32. And so this is 7.32, and they wanted it to nearest tenth, and so that's approximately 7.3 years. So that's how long it'll be to get to the population of 900 fish. Okay. Now, what is the carrying capacity for the fish population? Justify your answer using the graph of P. Well, our graph of P is on our calculator, so let's go back over there. And if we look at the graph, the carrying capacity is going to be where that line is. And so if we trace, we keep going up, and it keeps going closer. And basically, it's at 1,000. And so that's going to be our carrying capacity with as many decimal places as this calculator will show. So our carrying capacity then is 1,000, and so 22 is 1,000. But if you recall, this is the C, and the C is equal to the carrying capacity. So we could have got it directly from the equation they gave us, or we looked at our graph and it went up and then it plateaued, and that was our asymptote that y is equal to 1,000, and so that's going to be our carrying capacity for this fish model. All right, so hopefully that'll help get you some more ideas about how to use our equations to solve different application problems.